In this video, we will demonstrate the functionality of some of the Macnica IP components used in CMOS sensor-based designs. What you see on the screen now on the left is the incoming video, which for this demo is an extended desktop monitor output. The video is rotated 90 degrees, which is sometimes used for side-mounted surveillance cameras or when portrait mode output displays are used. On the right is an on-screen display. In memory, there are only 8 bits per pixel, allowing for simpler and faster rendering for the NEOS processor and reduced memory requirements. The video stream generated for this display is passed through a color palette, which converts the stream to 24 bits per pixel, thus enabling 16 million colors to be displayed from a palette of 256 pixel values. I'll start the NEOS application, and you'll see some color patterns which demonstrate the color palette. On subsequent screens, you'll also see that color is used for the various graphs. Now you'll see the familiar and rather uninteresting results for a blank screen. On the left is a partial view of the rotated extended desktop, and on the right is the on-screen display. In the on-screen display, the R, G, and B component histograms are displayed on the left side, and on the right there is, from top to bottom, a shading profile, a 2D graph of the chroma values, and a global luminosity plot. Now we'll add an Explorer window and walk through several tabs with various content. First, a Google homepage. Note that the Explorer window does not fill the screen, so the lighting profile reflects a single step and return to black. Most of the screen is very bright, as noted in the bottom right luminance chart, and the single chroma point shows that the CR and CB values are equal along an x equals y vector and are about half a full value. On the next tab, we have a monochrome gradient. Note the equal distribution for the R, G, and B components, the single chroma point in the middle graph on the right, and the gradient slope of the profile on the upper right. Now we have a red gradient. You can see that the red component has a uniform distribution on the upper left, and there's a very distinct vector in the 2D chromograph. In the shading profile on the upper right, you can see the increasing values of the red components. Now we have a green gradient. You can see that the green component shown in the left middle graph has a uniform distribution, and there's a new vector in the 2D chromograph on the right. Next we have a blue gradient. This looks different. You can see in the 2D chromograph that there is a triangular shape instead of a distinct line. There is also no prominence in the blue histogram on the lower left versus the graphs above it for red and green. Why is this? If I drag a little pixel value widget onto the display and scroll the mouse from top to bottom, I can see that the true blue values with no red or green contribution only exist in the upper portion of the image. The red and green components then become active and the pattern moves to pure white with maximum values for R, G, and B. This is also reflected in the shading profile on the upper right, where we can see a straight line of gradual increasing intensity followed by a steep ramp to saturation as the red and green components start to increase. And of course, the 2D chromograph is fairly interesting. Next is a color bar pattern. You can see the limited set of chroma values plotted on the 2D chromograph, representing the colors of each of the color bars. We can also see in the shading profile that the luminance is increasing for each of the bars. All of these components assist developers of CMOS-based sensor designs to analyze the content of incoming video in real time in order to control the hardware stages that implement shading control and correction algorithms. This concludes the video demonstration. Thank you for watching.